Hello everybody, hope you enjoyed the pedigree problem solving session. So now we will solve some RFLP, restriction fragment length polymorphism problems. Hope you enjoy that too. So RFLP, like you have already studied in one of the previous lectures, is important to study because it tells you the relative positioning of the restriction enzymes on a DNA sequence, and that is important when we want to clone a gene or subclone a gene into a vector. The exact location of the enzymes, the restriction enzymes is important to know. So one of the problems I will read here: the circular DNA molecule has cleavage sites for HIN3 and SMA1. From the accompanying diagram of an electrophoresis gel, draw a circular map of the restriction sites on the circular plasmid. So it has been, as we see in the electrophoretic gel, it has been digested, singly digested with HIN3, SMA1, and double digested with HIN3 and SMA1. So a single digestion with HIN3 gives a band of 3 kb and 7 kb. Also, as you see in the second lane where a single digestion with SMA1 has been done, also it gives a 3 kb plus a 7 kb band, and a double digestion with HIN3 and SMA1 gives two bands, one of 3 kb and one of 2 kb. So the total size of the vector here is 10 kb. So first let us draw a circle and the total size, which is 10 kb. Okay. So first let us look at draw a site, randomly draw a site for one of the restriction enzymes, which is SMA1. So here we draw so SMA1 gives two bands, one of 3 kb and one of 7 kb. So that is what we draw here, a 3 kb. So suppose the one site is over here and the other site is over here in the circular map, and so this is a 3 kb band, and this would 3 kb, and this would be the 7 kb band. Now if we look at the double digested products of HIN3 and SMA1, they yield a 2 kb and a 3 kb band, which is the total of which is not 10 kb. So that means that there should be two 2 kb and two 3 kb bands to make which adds up to the sum of the vector, which is 10 kb. So drawing a HIN3 site over here, which would give a 2 kb band according to the double digestion, HIN3 and SMA1, and another site if we draw it over here, so that will give us a band of 3 kb, a fragment of 3 kb, and HIN3 SMA1 fragment of 2 kb as mentioned here. So now if we add up all the fragments, if we look at the individual sizes of the fragments and see if the total is adding up to the vector, then we will know that our map is, the map we have drawn is correct. So SMA1 yields a 3 kb and a 7 kb fragment. So we will see here this is a 3 kb fragment and this is 2 plus 3 plus 2. So this is a 7 kb fragment. Again HIN3 gives a 3 kb and 7 kb fragment. So so this is a 3 kb fragment for HIN3 and this is a 7 kb fragment, 2 plus 3 plus 2 fragment for HIN3, and again double digest we are getting HIN3 SMA1 2 kb and HIN3 SMA1 3 kb fragments we are getting. So, this is a problem for a circular restriction map. This is the map that we just drew, and it looks exactly the same. So, next I will tell you about how to draw a linear map. So, the strategy is that one should look at the double digests, the new bands in the double digestion first, to look at the intermediate sites present between in a bigger fragment. So, let's draw a line, because it's a linear fragment. And if you look at the double digestion for BGL2 and BAMH1 first, we see that the new bands, which are black in color, there is a 3.5 kb band and a 0.7 kb band. So, now if you look at the BGL2 single digestion, there is a 4.2 kb band. So, it seems that that is being cleaved by BAMH1 site into two, 3.5 and 0.7. So, that is what we draw here. This is a BGL2 site and one BGL site over here. Okay. And this is being cleaved by a BAMH1 site over here. Say suppose here is the BAMH1 site which is giving the BGL2 BAMH1 0.7 kb fragment, and this is the one which is giving a 3.5 kb fragment. Okay. So, next if we look at the double digestion for the BAMH1 and PST1, here there is one single band that we see which is of 2.6 kb. So, if we draw PST1 site over here, let me change the color of the pen for your ease. So, here if we draw a PST1 site over here, so that would give us a 2.6 kb band for BAMH1 and PST1 over here. Okay. Now, let us look at the third double digest for, that is for BGL2 and PST1. Here we get 3 new bands, 3.3, 0.9 and 0.5 kb, rest are already there in the single digest. So, if we look at the the BGL2 single digest side, there is a 4.2 kb band in the BGL2 single digest, and it seems that that is being cleaved into a 3.3 and 0.9 kb band by a PST1 site. So, if we subtract 2.6 from 3.5, that leads to 0.9. So, this seems to be the 0.9 kb new fragment, and so 2.6 plus 0.7, which is equals to 3.3, is the other BGL2 PST fragment. So, what is left now? There is another band of 0.5 kb in the BGL2 PST1 digestion, and that means there is another PST1 site, and it should be on the other side of BGL1 hopefully. So, this is let me change the color again. So, if this is the other PST1 site, this could be the other 0.5 kb fragment, and if we see there are there is in the single digest for PST1, there is a 1.2 kb band which does not come up in any of these calculations. So, this would be the 1.2 single, since it is a linear cut DNA, this would be the 1.2 kb fragment for PST1, and the single digest of BGL2 shows a 0.3 kb band, which should come here since it is not coming in anywhere in between. This would be the 0.3 kb fragment. So, now if we add up all the or subtract all the combinations that we drawn, hopefully it comes up with the electrophoresis band pattern that we see here, and this is precisely what has been shown as the answer, and you can always practice it again and see if it comes up well. Restriction fragment length polymorphism can be used to has multiple applications. One of those is to predict what are the diseased, are there any diseased individuals in a pedigree if the parents are suffering. So, when does that happen? there are, like we've heard in the lectures about polymorphisms. These are mutations happening in the genome which introduces or deletes restriction sites in a gene, and which are also the basis of evolution. So it can basis of evolution, as well as it can cause to diseases. So like I show you over here, this is the diagram cartoon of a gene which I have drawn, a 5 kb fragment, and it has 2 restriction sites on either sides, which if the gene is digested with those, it leads to the 5 kb fragment. And here I have shown that a probe against a specific region of this gene, as you have learned in the southern blot technique in the previous lectures, will give you a band on the autoradiogram of 5 kb. But if there is a polymorphism occurring in this gene in some population, or in case of a disease, then it might introduce a new site into that gene, which leads to the formation which might not. So now when this gene will be digested with these 2 restriction enzymes, it will apart from the 5 kb band apart from generating a 5 kb band upon a partial digest, it will also lead to the generation of 2 other bands on a full digestion, one of 2 kb and other of 3 kb. So let us see, this is a pedigree of a diseased family which has a polymorphism. A female of the family is suffering, and if we see the, so what we want is that in the next generation we want to predict that whether there is a diseased individual, will there be a diseased individual in the next generation. So if you look at the banding pattern that we got from the autoradiogram that we got from the probe detection in southern blotting, the father, it gives a 5 kb band, which means that both the alleles, none of the alleles have that particular mutation which generates that new site, and hence there is only one single band. Both the alleles give the same, amplify at the same size. The diseased female, however, gives only one single band at 2 kb, which means that because of the restriction site generation, the probe can now detect only that particular fragment and not the 3 kb fragment. All right. Now let us look at the next generation. So the first individual is a male, and it generates a single 2 kb band, which is similar to the diseased phenotype of the mother. So that hints us that this might be a diseased individual. The other females in the family all have both a 2 kb and a 5 kb band, which means that one of the alleles is generating a 2 kb band, while the other allele is generating a 5 kb band, which means these are carriers for that particular polymorphism, and however they are not manifesting the disease. But the males in the generation have only a 2 kb band, which hints us that these 2 individuals might show the disease, might manifest the disease. So this is how restriction fragment length polymorphism helps us in diagnosing problems. Apart from this application, we all have heard about DNA fingerprinting, or also called as DNA profiling. Now what is the basis of DNA profiling? We have, like you can see in this diagram that I have drawn, these are gene segments which look pretty similar to each other. So these are nothing but tandem repeats which are tandemly arranged in a region of the genome, and these repeats are highly variable. The reason for them being variable is that one of the reasons is that during DNA replication, one of the strand, it straggles behind, and hence there is a problem in the pairing, in the base pairing. So what happens is that there is a slippage that happens, and there is a mispairing between, so pairing happens between the non-contiguous repeats. So that leads to either deletion of repeats on a strand or introduction of duplication of repeats, and that is what results in the variable number of the repeats, and that's the phenomena called as variable number tandem repeats, VNTR, that forms the basis of DNA fingerprinting. So here I want to show you that what happens happens as a result of this variable number. So you see in the upper panel there are restriction sites present flanking to both flanking to these regions in the orange color, and if we use a probe which is specific to the flanking regions, we get a unique a probe unique to the flanking regions, we get a unique banding pattern in both the unique banding patterns. As you see in figure A, it is giving since there are 6 repeats in one of the alleles and there are 4 repeats in the other allele. So, the restriction enzyme cuts at these restriction sites and hence generates different length of fragments. So, this is what we see 6 and 4 for A and 5 and 3 for for B. But what if we use a probe which is specific to one of the repeats and not the flanking regions, rather specific to the repeat region and not the flanking region? We will this is just 3 VNTR loci which I have shown, but we will get multiple banding patterns because a repeat might be present at variable regions in the genome. And this is what I have shown over here, that if we use a probe specific to the repeat region, it will show, for example, I will show you, I will explain you the green one. So, the green one has 9 repeats in one of the allele and 8 in the other. So, that is what we see over here, and in the individual B, the green one shows 8 repeats in one of the alleles and 6 in the other. So, this is the banding pattern that it shows upon amplification, upon detection. So, this is the kind of DNA profile what we get of an individual, obviously in a much larger number of bands that you see in a real DNA profile. This is just a cartoon to show you, to explain you the concept. And to show you about to tell you about the application, let us get into a crime scene. So, here you see an individual who has been murdered, and there are 2 blood spots as indicated in his surrounding, one near his head and one in the close proximity. So, we call the we type these 2 as blood spot 1 and blood spot 2, and the aim is to see whose blood is this, and does the blood help us in telling anything about the suspect who killed this man. So, the first step is type DNA profile, or like what I just told you in the previous slide, type the blood type of the fingerprint of these 2 blood spots. So, this is a particular banding pattern that you see in for both the blood spots. It's quite different. Okay, so that tells us that it comes from 2 different individuals. It doesn't just belong to the person who is killed. So now, which one of these belongs to the person who has been killed? For that, simply type the pattern for the victim's blood, and we see that the victim's blood is very similar to that of blood spot 1, which is near the head of the victim, which tells us that this is the blood, this particular blood spot comes from the victim who has been murdered. But what about the other blood spot? So, in this case, there were 2 suspects which in the vicinity, the police suspected 2 people, but it was not sure that which one of them killed this individual. So, blood was taken from both these individuals and their DNA profile was done, profiling was done. So, this is the DNA profile of the 2 suspects, and now we have to see that which banding pattern looks blood spot 1 is already of the victim. So, we have to match the blood spot 2 profile with these two suspects, and we see that the suspect 2 DNA profile matches almost exactly to the blood spot 2 pattern, which tells us that suspect 1 is innocent and 2 is the one who committed the crime. So, this is how DNA profiling using DNA fingerprinting is done to for paternity cases or for murder mysteries. One of the very popular the infamous case of Rajiv Gandhi assassination, where his murderer Dhanu was DNA profiled. So, what was done is that the blood from all over after the explosion, her blood was all over the crime scene, and that was taken and that was matched with the tissue on the belt, the bombing belt which she was wearing, and that was matched, and that was how it was confirmed that she was the one who detonated the bomb, and she was the one who was responsible for the explosion. So, this is how it helps in real life problems. So, this is all for today, and I really hope you enjoyed these problems, and see you in week 3. Thank you.